in answering any questions that you may have. But to start with, what I will do is we will quickly go over the course material, at least the initial part, covering first order logic. And Shikha and Bhaskaran will be on the lookout for questions. So, as and when we get in questions, we will shift our attention to the question and answer those questions. Essentially. Okay. And we have already got one or two questions. One is on lists in prologue, and at some point, we will address that issue as to how are lists represented inside any such representation scheme, essentially. Okay. So, uh, do we have any questions? Nothing to start with, right? So let's do a very quick coverage of what we have been doing in this course. So I'll share some slides which were not used in the course but which we can use now. Okay, and so as you can see, these slides are titled Knowledge Representation and Reasoning. They were made in a different context after I had recorded the course. And I would like to highlight some of the features that we have been covering in this course from this slide. So this is the first slide. This is also from my book, which on which this is based. And the basic idea here is that intelligent agents need to represent the domain that they are operating in. Yeah. So this is just a schematic which says that this gray figure is the domain, and this human-like figure is the agent, and that oval inside the agent's head is the representation that the agent is making. And as you can see, it's an approximation of the outside world. And in that representation, the agent possibly models itself also, essentially. So, since computer-based agents are digital entities, our representations are also symbolic in nature. So, I must emphasize at this point that this approach to symbolic representations is a little bit different from the approach which people use in neural networks, in which also, at least nowadays, when we talk about deep neural networks, we say that we have representations at different levels, but those representations are kind of distributed numerical in nature. Whereas by symbolic representation, we mean something which is explicit and where a symbol stands for something, as told to us by Simon and Newell, essentially. I think we are trying to just adjust our broadcast a little bit.
They cannot see the presentation, they can only see the title page.
Oh. Can you see the presentation? Can one of you respond on this thing?
They can see only the title page. One has responded.
Oh, okay. So let's see if we can get the representation going. The presentation.
This is not audible.
No, but after some time it was.
No, only first page. This is.
Can you switch to the presentation? Me.
So sharing is missing. This is what you were responding.
You can use the admin account to respond to queries and other stuff.
This is admin.
Yeah, this is admin.
Okay, this is respond. One person.
It had come on the screen as well.
Yes.
So, can you see the slides?
Yes.
But it's
Full screen not changing. You ask her.
So I'll use
It
it
says
in
it's
this.
fine. It's fine. It says it's fine.
You ask.
So,
Yeah.
so should I won't do
No,
presentation
sir.
No.
Present, sir.
in this.
Yes, sir.
In this mode.
Okay, so we won't do a presentation, so, and at least I think you can see the slides.
Not label.
So you can see.
Yeah.
Okay, great. So as you can see, uh, uh, the whole approach that we are following in what is called as classical AI or good old-fashioned AI is that we use symbols to represent things, and this has been the focus of our course in this. So, if you recall, Newell and Simon had said that physical symbol systems, a symbol is something which stands for something else, and a symbol system is a collection of symbols, and a physical symbol systems is something which also obeys some laws essentially. So, essentially, we are talking about representation and algorithms which act on these representations. Okay, and I'll skip through these slides because there are many slides, and I want to focus more on the knowledge representation part. And this is the slide where we started the course with, and we said that what does an agent know, and what else does the agent know as a consequence of what it knows. So this consequence is what we are interested in, and it's the aspect of making inferences that is important for the reasoning aspect of representation. And we have this whole field of study called semiotics, where we study about how things stand for something else. And there is also something called biosemiotics. For example, ants leave pheromone trails, and different kinds of animals leave different kinds of representations which stands for some territory and stuff like that. Reasoning is the manipulation of symbols in a meaningful manner, and we have started our childhood with learning how to add and multiply long divisions, and then eventually solving linear equations and so on. So essentially, we have procedures which act on symbol representations, and when we talk about logic, we are interested in inference procedures essentially. So why do we use something like logic? That
Just wait, sir.
Yeah, so just we'll see if we can get a full screen thing going.
Changing.
slides are also not changing.
Oh, slides are not changing.
Yeah, somebody said switch.
This PPT user. This.
Next.
Next. This.
Yeah.
No, here.
This.
Who said okay? Okay is for what? It's okay.
Now, can you see the slide?
Just 1 minute. Yes, sir.
Yeah.
Yes.
Yes.
Very good.
Okay, so I believe you can all see the slides finally. And so this is the starting point of the course practically. Is what we are interested in is what does an agent know, and what else does the agent know as a consequence of what it knows. Basically, what are the inferences that an agent can make about what it knows essentially. Can you see
Yeah. No.
representation?
Yeah. We can see.
It's a little bit delayed.
There's a lag.
Yeah.
There's a time lag essentially. Okay, so as I was saying, there is a whole field of study called semiotics, in which people try to understand what symbols are and how they can stand for something else, including symbols which can be biological in nature. For example, the pheromone trails that ants leave, and all kinds of animals make all kinds of markers in their natural world. And the manipulation of symbols is what we are interested in. And we start off by learning how to manipulate symbols, because very often when children do long division, they don't follow at the math level as to what is happening, they follow it at a symbolic manipulation level. And we often learn to do procedures without going into the depth. Why do we use why don't we use natural language like English for representation? And as this cartoon from the book by John Sova, the book is called Conceptual Structure, shows that very often we may be wanting to communicate something. So in this cartoon, the policeman is trying to give directions to some person, and the person is not able to quite understand. So basically, natural language is, while it is rich on the one hand, it is very verbose, and it can be imprecise, and it can be ambiguous, and which is why we need something like formal logic. So logics are formal languages with well defined rules for representation. So let us see what are the different kinds of logics that we can use. Uh, okay, so here on this slide we can see a whole variety of languages. At the center are these so-called classical two-valued logics. The simplest being propositional logic, then first order logic, and then second order logic. But there are also extensions to first order to classical logics, such as event calculus, where we talk about time and change; default logics, where we talk about what is a likely inference; probabilistic reasoning, which we don't cover in this course, but where we talk about probabilities and what is the likelihood of something being true. And then we have looked at subsets of logics called horn logics, which we used for defining tractable reasoning systems, which have been implemented in languages like Prolog. And also description logics, where we use a subset of the language which is also tractable, which can be used to construct ontologies and taxonomies and so on. And then there are other logics which talk about multi-agent systems. For example, epistemic logics talk about what one agent knows about what another agent knows, and temporal logics which talk about time explicitly, and various other kinds of things which we have studied essentially. Okay, so we will start with the syllogism, which is explains the fact that logics are formal in nature, that logical reasoning is evaluated or is said to be sound, or an argument is said to be valid if it conforms to a valid form. It's not the content which is so much important, it's the form. So these three arguments that you see, all men are mortal, Socrates is a man, therefore Socrates is mortal, all cities are congested, Chennai is a city, and if Chennai is congested, all politicians are honest, Sambit is a politician, therefore Sambit is honest. Now, when we talk about validity of logical arguments, and this is something very important, we are not so much concerned about what whether the conclusion is true or not by itself. What we say that in a valid argument, if the premises that you feed in are true, then the conclusion must necessarily be true. So if it is true that all cities are congested, and if it is true that Chennai is a city, then we can say that it is true that Chennai is congested. So it's conditional based on the premises. So if the premises are true, then the conclusion is true. So logic is a formal system. Essentially, we are only concerned with form and not concerned with content at all. Essentially, we evaluate a form to be valid or not valid, and the content is just incidental. It is something which is used by us to put logic to some useful purpose. So we may model certain domains in which we want to do reasoning. So, for example, students in a university or number systems or whatever the case may be. But the focus is on good formal structures or good forms which are valid forms of reasoning. The simplest form of logic is propositional in nature, and we started the course with that, in which a sentence is an atomic entity. For example, we use symbols like P, Q, R, and it can mean anything we want it to. So P can stand for anything, can stand for anything, and so on. It is not concerned with logic, is not concerned with reasoning essentially. Uh, and and in propositional logic, the sentence is the atomic unit, and we can't look inside the sentence. So if we have a sentence like all humans are mortals and Q is all women are mortal, and if we are told that P implies Q is true, then we can infer that Q is true. But if somebody says that R is a sentence which stands for Suman is a woman is true, we cannot infer that Suman is mortal, because of the fact that in propositional logic we cannot look inside sentences. We can only take the sentence as a whole, and there is no sentence in our knowledge base which has P and Q and P implies Q which says Suman is a woman essentially. It says all humans are mortal, all women are mortal, and that kind of stuff. So for that, when we want to look inside sentences, when we want to break up sentences into the constituent parts, we need first order logic essentially. So in first order logic, for example, we can talk about stories in which we can say sentences like the culprit stole the document. Now the culprit is a variable. We don't know who the culprit is, and so in first order logic, we represent the culprit by saying that there exists somebody who must be the culprit essentially. And the notion of variable and quantifiers over variables is introduced in first order logic, and we'll do a very quick review today again. Then we spent a little bit of time studying description logics, which is the logic of noun phrases. And I had observed that there was a considerable amount of discussion going on the forum, which Bhaskaran was handling. And Bhaskaran is an expert in description logics and ontologies. And if there are any questions today, we can clarify them again, essentially. We also spend a little bit of time in default reasoning. Default reasoning we do when we want to make inferences without having to take resort to universal statements. So when we say birds fly in general, it's not a universal statement. A universal statement would say that all birds fly, but a general statement says that birds fly in general. Now, how does one represent these general statements? Because the quantifiers that we talk about in first order logic, the existential quantifier and the universal quantifier, it's not sufficient to discuss things like that birds fly in general, that leaves are green in general, that students are bright in general. We can make a statement that all students are bright, and that can be expressed in first order logic by saying for all x, if x is a student, then x is bright. Or we can even say that some students are bright, which is that there exists an x such that x is a student and x is bright. But we cannot make statements like most students are bright or in general students are bright. And for that we have to resort to special kind of logics called special kind of reasoning called default reasoning, and we did spend some time doing that as well. Sorry.
It says, can you explain forward chaining and backward chaining in a simpler way?
Yeah, I think so. There is a question which has come, which talks about forward chaining and backward chaining in a simpler way. So let me actually kind of jump to that. Should I just go in the slides? I have some slides which talk about forward
Yeah,
chaining.
yeah, I think.
So we'll quickly move over to first order logic, uh, and we'll address the question which has been asked, which talks about forward chaining and backward chaining.
Yeah, from the algorithm standpoint, he says. So
Yeah.
implementation, implementation standpoint.
Hmm.
How
Okay. Epistemic reasoning was about reasoning about what other agents know. So let's talk about first order logic. So I'll skip over some of this basic stuff where we talk about what do you mean by provability and what are rules of inferences. So these are, for example, rules of inferences that you are familiar with, and the notion of proof of forward chaining or backward chaining is tied up to such rules of inference. So the leftmost rule of inference that you see on the top left corner, which is the most commonly used rule, which is called modus ponens, and the modus ponens rule says that if you have a sentence of the kind alpha implies beta, where alpha and beta are any sentences in first order logic, and you have a sentence alpha, then because this alpha matches with this alpha in the uppercase, we can infer beta essentially. And likewise, there are other rules of inference like modus tollens conjunction and so on, which are used in generating proofs essentially. And there are rules of substitution which say that A implies B is equivalent to not A or B, for example, and things like that. So A implies B, or alpha implies beta is equivalent to not beta implies not alpha, or alpha implies beta is equal to not alpha or beta. So essentially, as I said, logic is formal in nature, and you have to have these algorithms to manipulate formal representations. And the formal representations are in the language that we are talking about. In our case, it's going to be first order logic most of the time. Then we have this notion of proof, that you can keep making inferences, keep applying rules of inference, and eventually you will come to the goal. Now, we will go into this in a little bit more detail a little bit later, but forward chaining is what is depicted in this diagram. Is that in the circle what you have is a knowledge base, and these arrows represent applying rules of inference. So you start with what is given to you, and then you move in a forward direction till you have reached what you want to prove essentially. And this process is called forward chaining. We'll look at forward chaining and backward chaining shortly again. I'll skip the semantics part here, but essentially semantics deals with truth essentially, and you want to say when is a sentence entailed by a knowledge base. So we say a knowledge base entails alpha if it is necessarily true whenever the knowledge base is true. And in some sense, we can have a set of true sentences, and we can have a set of provable sentences, and we define the notions of soundness and completeness, which was kind of connected the two. A logic is sound only if only true statements can be proved, and a logic is complete if all true statements can be proved. And we had discussed that first order logic is sound and complete essentially. So essentially, this in this diagram, what you see is the green dots are the provable statements, and the squares are the entailed statements, and ideally they should overlap. For every green dot, there should be a square, and so on. In which case, it will be sound and complete. What is depicted here is a logic which is neither sound nor complete, because there are statements which cannot be proved, and there are false statements which can be proved. So we'll skip over the syntax, and I'm sure you're familiar with the syntax by now, and we'll move to the process of reasoning.
backward chaining.
Yeah, forward chaining and backward chaining.
Backward.
Yeah. So we'll skip some of these things. So one thing you must also remember is that in the process of manipulating uh, formulas in first order logic, we typically use two extra rules. One is called the rule of universal instantiation, which says that for all x, if something is true, then it must be true for a specific individual a, which is a constant in the language. Likewise, if something is true for a specific individual, we can infer that there exists an individual for which px is true. And this is an example here. and that we used in the Socratic argument. Essentially, we said that for all x, man x implies mortal x, and we could therefore infer man Socrates implies mortal Socrates. And then, given the fact that man Socrates is given to us, we could apply modus ponens and do that essentially. Okay, so we had rules of substitution and so on, and we had in propositional logic we had said there is no semantics, we just have set of symbols, and in first order logic we have something called interpretation, which I will skip over for the moment. But basically, and we'll come back to interpretation when we talk about incompleteness of first order logic, or certain algorithms in first order logic, uh, and we know how to assign truth values to formulas and so on. But we are more interested in the reasoning process, or the process of finding uh, proofs essentially. So let's start with this process of formal of a proof in propositional logic, and we'll come to we start with forward chaining and we will come to backward chaining a little bit later. So in this uh, diagram that you see, uh, the first four sentences are given to you. These are called premises. So P and Q, P implies R and S implies T, and not Q or S. What you are required to prove is the sentence T essentially. And this process of moving from data towards the proof is the process of natural deduction, also called as forward chaining. So where is forward chaining happening here? So if you look at this formula P and Q, from there you can infer P because there is a rule called simplification. You can also infer Q because there is a rule called simplification. And then because we have P and because we have P implies R, we can infer R by modus ponens again, and we can infer S because from not Q or S.
The question for Rete, can you explain that?
Yeah, we'll come to Rete algorithm after we are done with first order logic. There is a question on Rete algorithm. Uh, I don't have slides for that, but we can do it on the this thing. Sorry.
No, that's a question.
Okay. So let's first focus on this thing. So the first order version of forward of this story about one student uh, has these sentences. So Alice likes maths and she likes stories is represented by likes Alice maths and likes Alice stories. If someone likes maths, then she likes algebra. Can be written as for all x likes x maths likes x algebra. So it's the same story except that we have these first order logic statement, and then we have this notion of proof, which involves this rule of universal instantiation. So this is the process called natural deduction. So now let's come to the question that was asked by someone as to explain forward chaining and backward chaining essentially. Now in forward chaining you are given something that all P's are Q's, and you are given that A is a P, so which is represented by the fact that P of A, all P's are Q is represented by for all x Px implies Qx. Now in forward chaining you move from data to conclusions. The conclusion is you have to show that Q is A. For example, P could be man, Q could be mortal, and the first statement would be read as all men are mortal, and P of A would mean Socrates is a man, and then you have to show that Socrates is mortal. So forward chaining is in first order logic is a two-step process which we later compress to a one-step process using the unification algorithm, which we will see if we get time to discuss later. So in the implicit quantifier form, we keep only universally quantified variables. So the first statement which says all men are human beings is written as man question mark x implies human question mark x. So question mark x is an implicit form for saying that an algorithm, that a variable is universal. So we developed this in implicit quantifier form, and we looked at how to convert uh, statements into implicit quantifier form, and then we use the process of unification. So the same statement which says that all p's are q, and if a is a p, then a is a q, in implicit quantifier form can be done in one step, provided you have this algorithm for finding a unifier. So what is a unifier? A unifier is a substitution for a set of variables such that two formulas become the same, or they are unified essentially. So in our case, we want to unify this formula p a is a p bracket a with p bracket a variable x, and this unifier can be found by saying that you can substitute x for a, and then this will become equal to p of a, and then you can apply the unifier to the right hand side, and you will get the answer q of a. So we had this process of unification which we had discussed, and in general we can see that we can get a shorter proof in implicit quantifier form than a longer proof which involves this extra step of universal instantiation. Okay, so then we had at some point said that the unification algorithm should be such that it gives you the most general unifier, but we'll skip that part here essentially. So I'll skip over the unification algorithm and come to the questions that have been asked. And this algorithm can be found in many different places. Okay, so the process of forward reasoning has been done in forward chaining rule based systems, and in this context we had looked at the Rete algorithm, which we will come back to later once once we are done with discussing backward chaining. And in rule based system we have rules of this kind. If the left hand side is true, then there are some actions one can do on the right hand side. So this is a small rule which can be used to interchange two elements in an array, and it says that if the element at index I has a value n, and if an element at index j which is greater than I has a value m which is less than n, then you should exchange the values by saying that the first value should become m and the second value should become n. And this is a kind of language which a forward chaining system uses, a rule based system. Uh, and we had discussed some systems which were used in forward chaining. So as I said, the difference between forward chaining and backward chaining is that in backward chaining we move from goal that has to be proved towards a fact. That is, if you are given a statement of the kind alpha implies gamma and a goal beta, then we infer a goal alpha theta, where theta is a unifier for gamma and beta. So gamma is the right side of the implication statement, beta is a goal that you are interested in. So if you can find a unifier which will make this beta equal to this gamma, and if that unifier is theta, then we can infer a sub goal of alpha theta by applying the same theta to the formula alpha. So this is the process of backward chaining in first order logic. You are given the statement that all p's are q, and you are asked the question that is a q, or can you show that a is a q, which is like saying that we have a goal to show that q a is true. In backward chaining we move backward in this fashion to reduce this goal to a new goal which says that can you show that a is a p, and that can be shown trivially because it's given to us in the knowledge base that a is a p. So backward reasoning is goal directed, and we are only interested in finding out what are the inferences we need to make to show that that particular goal is true. Whereas forward chaining is data driven, and in general we keep making inferences which are true, but they may or may not be leading to what you want to show to be true, which is the goal, and which is why many people say that backward chaining is more efficient than forward chaining. And in fact, it's a foundation of the logic programming idea, and the foundation of the language Prolog that we have also discussed in this course essentially. Okay, so supposing we have we are given this statement, all men are mortal. So remember that in the implicit qualifier form, that statement would be represented as man x implies mortal x. So when I say x, basically it's a variable. I am not pronouncing the question mark. So man x implies mortal x means is just an implicit quantifier form for stating that all men are mortal. Now if you have a variable in a goal, for example mortal z, then the implicit quantifier gets reversed. So this is a convention you must remember, that in a goal clause variables implicitly are existential in nature, which means we are asking the question, is there someone who is mortal? Now this is something which is very similar to what you do when you look at databases and you implement database systems. And in database systems, you often ask queries about, is there an employee who earns more than 20,000 rupees and whose age is less than 21 or something like that. So these kind of questions you can ask in database questions. So these are existential questions which say that, is there somebody in the domain who satisfies certain properties? What database systems cannot do is to make inferences in the process of answering questions. Database can systems can only retrieve what is there in the database. Whereas when you combine database systems with logic programming, then you can make inferences and answer questions as well. So for example, if you are told that all men are mortal and you are given a list of people who are men, and then you are asked this question, that is there somebody who is mortal, then in backward chaining the first thing we do is that we move from the goal of being mortal, or to go the goal to that show that someone is mortal, to the goal that someone is a man. Now this is the process of backward chaining, except that in this case we had a variable in the goal, and that variable is treated as an existential variable, which means that you want to say, does there exist somebody who's mortal? And we have reduced that question, that is there somebody who is mortal, to the question, is there somebody who's a man essentially. And this is done by a process of backward chaining. And now if you had knowledge base that Plato is a man, then you could show that yes, Plato is mortal. Or if you had in your knowledge base Socrates is a man, then you could show that Socrates is mortal. And likewise for any other person who is a man essentially. So if you have done programming in Prolog, you would see that once you get one answer, for example, is there somebody mortal, and the system might come out and say yes, Plato is mortal, you can ask for the next answer. Typically in Prolog, that is done by pressing the return key, and then it gives you a next answer and next answer. And this is the process that it follows in Prolog, which is the sort of backward chaining essentially. So when we are given this knowledge base, this is a knowledge base we started off with in propositional logic earlier, and we are asked this question. Then in backward chaining, we start off by saying that show that is T true. So this is a knowledge base given to you, which I have written here again. P is given, Q is given, P implies R and S implies T, Q implies S, and not U or not V. So we have broken down this knowledge base to simplify it by into clauses. So instead of P and Q, we have just written P separately and Q separately, which is an equivalent thing. So in backward chaining, you work with goals. So if T is the goal, then we reduce it to a different set of goals, which is R or S. How did we do that? We did it by using the rule, the sentence 4, which says that R and S implies T. So in backward chaining, we say, okay, if you want to show that T is true, then better go and show that R is true and S is also true, which in this goal set is seen as a sub goals. We can call it sub goals R and S. Now to show them, we can in turn to show that R is true, we can use the rule P implies R, and say that to show that R is true, show that P is true. So now our goal set has become P and S. Then P is given to us, so that's already true. So now we are left to show that S is true, and S in turn can be reduced to Q by, because there's a rule which says Q implies S, and to show that S is true, we have to reduce that, show that Q is true. But Q is given to us, and therefore we have the empty goal set, and therefore we can say that yes, T is true. So backward chaining is different from forward chaining, because we work from the goal and eventually show that that goal is true. In forward chaining, we would have started with the data and eventually said that yes, we can add T to the knowledge base. So that's the difference between that, and we can extend that easily to first order logic. So if we had a rule which says that all P's and Q's are R's, then we, in backward chaining, we would say that if you want to show that R is true, then you should show that P is true as well as show that Q is true, essentially. So this is the process of backward chaining, and this creates a kind of a search tree which is called an AND/OR tree, which is illustrated with another problem here. Uh, so at the bottommost line, you can see what is given to you, which are facts. The facts are A is green, B is green, C is a circle, E is a circle, C is red, D is red, and D is a square. And the query is that is there a nice toy in your knowledge base? And there are two rules that are given to you. One rule says that if something is green and it's a circle, then it's a nice toy. And the other rule says that if something is red and it's a square, it's a nice toy. Then you can see that the backward chaining engine would search through a tree like this and eventually come up with an answer. So it will start off by asking, is there something which is a nice toy? And then first it will try the left hand side and say that, okay, is there something which is green and which is a circle? And then it'll find that yes, A is green, and therefore it'll ask the query that is A a circle? Now, but that would fail because A is not listed as a circle. So it will backtrack and try if because B is also green, it will try to see whether B is a circle, and that will also fail. And therefore we have run out of all things which are green, and at this point we will move to things which are red, and so we are now looking for something which is red and which is a square. So first we try C, because this is doing in a depth first fashion, and we have spoken at various times that Prolog essentially does depth first search on such a tree, which is called a goal tree. So first we try C, which is red, but red is but C is not a square, so that fails. And eventually, when we say is D a square, and we succeed, and we are left with the empty goal, and at that point we can answer that yes, D is a nice toy according to the definition that has been given here, because D is red and D is square, and this was one of the two definitions we had chosen for noise, right? So the solution of an AND/OR tree is a subtree, as we have discussed earlier, and then we can discuss other bigger problems. At this point, I just want to spend a little bit of time on discussing this issue of completeness, essentially. So we have understood what is forward chaining, and we have understood what is backward chaining. Uh, in forward chaining, you move from data to what you want to show, and in backward chaining, you want to show go from what you want to show to the data, essentially. And we have also tried to emphasize the fact that logic is formal in nature, and meaning is not involved in reasoning, essentially. So if you are given this knowledge base, and the knowledge base, so this is a notation that has been borrowed from Charniak and McDermott. O is the name of a predicate, and A and B are arguments. So O of AB is true. Likewise, O of BC is true. M is a predicate, and name A is the name of the argument, and M not of MA is true, and M of C is true. What is this knowledge base talking about? in logic, as I have been saying repeatedly, content is not important. The form is important. If you want to show something to be true, then we have to show that there is a formal way of showing it to be true. The meaning is not important. Meaning could be anything. So, for this particular set of statements, we can have different interpretations. We can have a Bloxwell interpretation in which O stands for on and M stands for maroon, and ABC are names of blocks. Uh, so the first statement says A is on B, the second statement says B is on C, the third statement says A is not maroon, and the fourth statement says that C is maroon. So it could mean that, that means if you have some interpretation like this, uh, that is the meaning of those sentences. Uh, let us say the query is, so we don't know what is the color of B essentially. We could have a different domain and a different interpretation in which ABC are people, so Jack and Anne and John, and O stands for looking at, or and M stands for married. So the first statement says Anne is looking at John, uh, looking at AB. A is Anne and B is John. The second statement says Jack is looking at Anne. The third statement says, or the fourth statement says that John is married, and the third statement says that Jack is not married. Now,
Total duration was 1 hour.
okay, so I'll wind up soon.
We'll take one 15 minutes extended terms.
So we'll take another 10, 15 because there's one more question which has come we want to answer. Right? So if given this knowledge base and given this question or the goal, that is there an x and is there a y such that oxy is true and not of mx is true and my is true, then we can see that it's clearly the case. In the blocks world, the questions are: is there a non-maroon block on a maroon block? In the people world, the question is there a not married person looking at a married person? And if you look at the the, the statement, that clearly there is a block which is not maroon and which must be on a maroon block, because there are only two cases here, that either B is maroon or B is not maroon. If B is not maroon, then B is on C and it satisfies the query that there is a non-maroon block sitting on a maroon block. On the other hand, if B is maroon, then B satisfies the query that there is a non-maroon block sitting on a maroon block. So in either case, the sentence is true. Unfortunately, neither forward chaining nor backward chaining can arrive at this proof. And what we did in the rest of the course was that we introduced the resolution method and showed that there is a method which is complete for first order logic, and we had done this details, and I will just show the proof for that. So these are some of the resolution proofs that are there for this thing, and we had gone through a process of converting into clause form and everything.
So there's a question on people are asking for previous year's question paper, and we have replied saying that it's similar to assignments.
Yeah.
And how to prepare for the exam is one question.
Yeah. So I think there have been some queries about what is going to be the nature of the final exam. And our response to that is that if you have done the assignments, you will find that the final exam is very similar to the assignments. And in fact, it might be just a little bit simpler than the assignments. So if you have done the assignments properly, you should be able to do the final exam easily, essentially. Okay, so I'll just quickly skip over this. This is the resolution proof for the our classic question: all men are mortal, Socrates is a man, and therefore. So you can see that this resolution proof can be seen as forward chaining part here, or it can be seen as a backward chaining part here, where we take the query and reduce it to another query. And what is more important is that for the problem that I just discussed, which is this problem of answering this existential query, the resolution method is complete. And first we convert everything into clause form. So we have all these four statements that were given to us, and then we have the negation of the query converted into a clause form, and then we can do a derivation of the null clause uh, as follows. So in the blocks world, we can show that we derive this, we derive this, we derive this, and so on in the null clause, and you can work it out for yourself as a small example. Likewise, in the domain, the derivation can be done, and therefore you can show that this is a complete method. Okay. After that, we had done a little bit of logic programming, which is based on backward chaining, and there was a query which had come to us about what is a list and how it is represented inside logic. So let us focus a little bit upon that a little bit, and the the answer to that question is that lists are essentially binary trees uh, in internal representation. So it's not just in logic programming, but in most languages, lists are represented internally as binary trees. So if you have a list which we write as a list of two elements A and B, then we have a notation which comes from uh, various sources. Is that uh, we can see this as a tree in which the root has two children. It's a binary tree, remember, and the left child is an element and the right child is a rest of the list. So such a structure is called a cons pair in, and it came from the language Lisp originally. So if you look at the lower cons pair, it corresponds to cons of B with nil. So this is an empty list, and there's a element called B. If you put B with an empty list, you get cons of A comma B. Now this whole thing is the rest of the list for the original list. So we have cons of A with cons of B comma nil. So cons of A with this, and this itself is cons of B comma nil. If you had a larger list like this, A, B, C, D, then you would have it as cons of A with cons of B with cons of C with cons of D. But as you can see that this is basically a binary tree of this kind essentially. You can construct T structures for more complex lists, nested lists, and so on. It's possible that the left hand side is itself a list. In the case, for example, where you have a list like AB as the first element and C as the second element. But essentially, it's a binary tree essentially. Yeah, so here's the example of this third element. A nested list being the first element, so that you can see here as a list containing A and B, which is what we started off with, and that is the left side of the binary tree, and the rest of the list, which is a list containing C only, is the right hand side essentially.
We have provided a web resource
Hmm.
for Prolog in general, and this also contains list process.
Yeah, so Bhaskaran is saying that on the forum we have provided a web resource for Prolog web resource, and that web resource also has material on the list essentially. So please do go to the forum and look for this mail message from Bhaskaran, which talks about how Prolog is, what is Prolog, and how lists are used in Prolog essentially. In the class, we had done an example of showing that how backward chaining can be used for doing append of two lists. So if you have a list containing AB and if you have a list containing CD, then you can get a new list. And in backward chaining, this is asked as an existential query, that is there a list called X such that when you concatenate AB with CD, or when you append AB with CD, then you get X. And essentially backward chaining constructs an answer, and that I think we have done in class. So we'll skip over this part, and maybe I should just spend a little bit of time on written it. Or would you like to do the written it or something? How do I go to the
I'll tap.
that
Journal.
Journal. Yeah.
just for a few minutes?
Right, sir. See the journal.
No, we don't.
What was the question on the written it?
Explain written.
Plain writing.
Explain the full written it. Well, I don't know whether we have time to explain the full written it. But while we set up this
Can you explain the Rete algorithm?
the Rete algorithm essentially. Okay. Now let's just do a very quick recap of what the Rete algorithm does. Uh, in forward chaining rule based systems, can you read? The high level algorithm was match, and what match did was it took as input a set of rules, and it took a working memory, and it produced what is called as a conflict set. And then this conflict set was input to a module called resolve, which selected one matching rule along with its data. Uh, and that was a separate process of conflict resolution which we studied. And then it gave us one rule plus data. Data is the working memory elements, and it was sent to a module called fire, or maybe we called it execute. And what this did was to produce some new working memory elements and delete some working memory elements. Now, the problem with the brute force approach of this high level inference engine is that this match has to look at all working memory elements and all rules. So it has to do a tremendous amount of work, and it has to do this in every cycle of this thing. So if you remember, a rule based system works by taking a rule with matching data, and this is done by the match algorithm, selecting first doing the match to find out what are all the rules which are applicable. That's done by match. Then selecting one rule in the resolve phase, then executing that rule and producing some new data or deleting some old data. And in the brute force approach, this match has to do this all the time. With every working memory element, with every pattern in the left hand side of a rule, it has to see whether that matches or not, and then construct the conflict set all over again. So what the Rete algorithm does is it replaces the match part as follows: that the rules are already compiled into the Rete net, and what the input to the Rete net is changes in working memory, and what it outputs is changes to the conflict set. So this is the motivation for the Rete algorithm, is that in every cycle we do not want to match the entire database or the entire working memory or all the set of all working memory elements with all the rules. And remember that each rule will have a certain set of antecedents left hand side, and you want to match with all of them. And because when you select and fire just one rule, it makes just a small number of changes in the working memory. It may delete one or two working memory elements, and it may add one or two working memory elements. The rest of the working memory does not change. So the match algorithm is repeating the work it did in the earlier cycle, in which it matched all these working memory elements with all the rules. And what the Rete algorithm allows you to do is to only look at changes in the working memory element. What are the changes in the working memory element? Changes in the working memory element are the plus or minus that you are adding to that, and only analyze those in some sense and give you changes in the conflict set. So how does it do that? Let me sort this out. It's okay. I wanted a new page, I think. So I'll just give you a quick this thing. The RateNet is a compilation of rules, and it has two parts. The top part is discriminative in nature. It's like a generalization of a decision tree or a KD tree or some of those things that you may have studied. And the bottom part is assimilative in nature. It tells you what is matching or not. So the important part is the top part, and it works like this: that you ask a question, what is the class name? So remember that the left hand side of a rule will have different class names. So you may say pyramid or student or whatever. And so if there are, let's say, 4 classes, C1, C2, C3, C4, then what this does is that it, supposing a new working memory element has come, we call it as a positive token. So when a new token comes in, it falls down into this network, and based on what is the token. So for example, the token may be student, name, let's say Suresh, subject, let's say physics, marks, let's say 30. So this could be a token. So first it looks at the class name and sends it down one. So let's say C1 is equal to student. So the token has come here. So the next question it might ask is what is the subject? So you may have physics, you may have chemistry, you may have maths. So this particular token will come down to this physics path, and then you might ask marks. So marks might be in ranges. So it may be 0 to 40, it may be 41 to 60, it may be 61 to 100. Let's say we have only 3 ranges. Then this part will match, will answer this question as to what is the marks. In this case, the marks are 30, so the token will go down in this direction. And there is also one something which will be named. So uh, typically we do not expect student specific name. So the name may simply be X or something like that, and therefore the match algorithm will say for this case X equal to Suresh, and it will send the token down. So this is the basic idea of a Rete net, is that once you throw a token into the net, then based on what the token contains, it traverses down the discriminative part of the network and it will go down some place. So now if a rule has three patterns P1, P2 and P3, then eventually this rule will need one token which is of type P1, one token which is of type P2 and one token which is of type P3. So if those three tokens which match this particular rule are thrown into the network, so one could be, for example, this student token, and the other tokens could be something else, uh, maybe age of the student or some other information. And if you, so maybe one token could be cutoff marks for various things and so on. And once you get those three tokens here, then we say that this rule goes into the conflict set essentially. So in the Rete net, when you construct the network, it is constructed only by looking at the set of rules essentially. And then you have the Rete net, which is a compiled network. Then once you throw in the data one by one from the top, it percolates down into the network and eventually it activates all the rules which it matches essentially. Then when one of the rule is selected and executed, it produces those plus minus changes into working memory. And when those tokens are sent down into the network again, you must remember that all the other tokens are already sitting in the net. So all the other data which was matching the different rules are already there in this network somewhere in the conflict set, and only these new changes are percolated. So in that sense, the ReteNet saves you from doing this brute force match all over every time essentially. That's the basic idea of the Rete network essentially. Okay, so I hope today's session was useful. Because we had very few questions, I took the opportunity to kind of go over part of the course very quickly. And the forum is still alive. And if you have any questions or any doubts, please do come to the forum, and the three of us will try to answer your questions. And we look forward to you doing well in the final exam on the 27th, and wish you all the best.
In fact, recently people started asking more fundamental questions. So we
Yeah,
have been
I
posting.
think Bhaskar is saying that he's very happy with this current batch of students, and many of them are asking very fundamental questions, which is good. And I hope that you all go on to do good work in the field of AI in general and knowledge representation in particular.
Posting the slides. There was one request to put these slides up on
These two slides, or those whole slides,
these.
Some, yeah,
This
the
slide.
slides that
written it slides.
The main.
No,
Yeah, I can post. We can post the other slides.
once we have discussed with
Yeah,
the ones.
sure, sure. Okay, so wishing you good luck for your final exam. Hope that you do well. So we are signing off now.